Welcome back in this online summer school on galaxies and cosmology. So thanks everyone for joining us in this session. It's my pleasure to welcome Dr. Masamune Oguri from University of Tokyo. He's my colleague in Japan. And now he will give us a lecture about the introduction to weak gravitational lensing. So especially for full participants, I hope you can enjoy, I mean that you can make a full attention for this lecture because Oguri-san also will provide you with workshop materials next week. So please be attention in this lecture. Okay, before we start his lecture, I will read his short CV. Now, he is assistant professor in Research Center for the Early Universe in University of Tokyo, also associate scientist, Kavli Institute for the Physics and Mathematics of the Universe, Kavli IPMU, also in University of Tokyo. He got his bachelor until PhD degree from University of Tokyo, and his research field is cosmology and cosmological structure formation, especially topics related to dark matter and dark energy. And then he also studied the dark universe mainly using gravitational lensing, taking both theoretical and observational approaches. So yeah, I wanna welcome Oguri-san. Please, time is yours.
Okay, thank you very much for the introduction. So I share my screen. Okay, so I'm giving a lecture on weak gravitational lensing. Weak gravitational lensing. I think you already had lectures on cosmology and gravitational lensing. So I think you are kind of already familiar with the basics of those stuff. But I will also try to explain this cosmology and gravitational lensing from scratch so that you can follow my talk. Okay, so this is the plan of my lecture. So I will give a general introduction and explain lens equation first, and then explain weak lensing shear and convergence. That are two basic quantities used for weak lensing analysis. And I explain tangential shear and show the example of analysis using this tangential shear and how we can extract information on, for example, cluster of galaxies from this tangential shear analysis. And finally, if I have time, I will explain weak lensing mass map. Okay, so I think you have already learned this, but as you know, this is the standard cosmological model. From various observations, we know that this universe is dominated by unknown components called dark matter and dark energy. So roughly dark matter consists of like 30%, 30%, 27%, and the dark energy consists of 68%. And although we cannot directly observe these dark components, we believe those dark components exist because by introducing these dark components, we can explain many observations in a consistent manner. So we believe those dark components exist, but it's very hard to study these dark components because we cannot directly observe them, for example, by pointing telescope. So gravitational lensing provide a very powerful means of study this dark universe, because this is purely a gravitational effect, so that we don't care if this lens is a dark or luminous matter. So if there is a dark matter, so gravitation ranging like this. So suppose there is some distant object, and there are some foreground massive object like a dark matter. Then light emitted from this distant object go travel like this. But due to the presence of this lens massive object, light ray path is reflected by this dark matter or matter distribution. So this light ray do not travel just straight, but like this, deflected, and eventually reach Earth. So this is gravitational ranging, and this produces a distortion of the light ray path. And in addition, this also produces a distortion of the observed shape. So this is the original shape of this galaxy, but this shape is distorted, also distorted by this gravitational ranging effect. So I think you have already seen many these kind of pictures. So this shows ranging effect. So as you can see, this is a highly elongated object, and this high elongation is produced by gravitational ranging. And this central one, you can see this blue ring-like structure. This is a small distant galaxy, but due to the gravitational ranging effect, we see this galaxy like this ring, like this. And again, this is also a highly elongated distant galaxy behind this galaxy cluster. And this lower left one, this one, is also a famous gravitational lens system. You can see several elongated arcs like this, and this looks like a cat. And this one is an image from Subaru Supreme that I took many years ago, and this also shows us this kind of elongated background galaxy shape. So I think you have seen many of these, but important thing is that all these are strong gravitational ranging. So you can clearly see this ranging feature by eye, but all these are strong gravitational ranging. So, so what is weak ranging? So weak ranging is a very tiny distortion. So distortion is very weak because gravitational field is very weak. So for example, in this figure, so this upper left corresponds to the center of a cluster of galaxies, very massive object. And because dark matter is so concentrated that the ranging effect is very strong around this region. So you can see this highly elongated galaxy by eye, and these are strong ranging. But even if we, apart from this very massive region, for example, this lower right corner where the gravitational field is much less weak, although you cannot see any obvious elongation of galaxies, but if you analyze shape of galaxy statistically, then we can still detect ranging effect, and this is called weak ranging. So weak ranging, you cannot detect, you cannot see detect by eye, but by doing some sort of statistical analysis, you can detect this tiny ranging signal. So this is weak ranging. So again, this is weak gravitational ranging, or sometimes we call this weak ranging. So as you know, except for very rare cases, ranging effect is very weak, and we cannot see this weak ranging effect by eye. But because this signal is hindered by intrinsic galaxy shapes, so if all the galaxies have circular shape or spherical shape, then we can we may be able to detect ranging effect even if it is weak. But galaxies are not like that. So as you know, this Milky Way galaxy is also a very disky, have this disky-like structure, highly elliptical. And many other galaxies are also having elliptical shape, intrinsically elliptical shape. And there is a ranging effect on top of this intrinsic elliptical shape, but its signal is so weak that we cannot directly detect it. But by averaging the shape of many galaxies, we can still detect this weak gravitational ranging. For example, this cartoon shows idea of this weak ranging. So these are the intrinsic shape of galaxies without any ranging. And by adding ranging effect, each shape of each galaxy is slightly deformed or distorted. But this weak ranging signal is usually much smaller than the intrinsic shape of galaxies. It's very hard to see by eye. But by averaging these galaxies' shape, assuming that the orientation of each galaxy is random, then this intrinsic shape averaged out, and we can extract this ranging distortion. So this is a basic idea of weak gravitational ranging. So this is just showing an example of weak ranging analysis. We can, as I said, we can use these shapes of many galaxies and do some statistical analysis. We can extract or study the dark matter distribution in cluster. So this figure shows total matter distribution inferred from weak ranging. This blue color shows the density of dark matter inferred from this weak ranging. And you can see indeed this, so you can see this strong ranging feature in this image. So we know that dark matter is concentrated around this region. But by doing this weak ranging analysis, we can also say that the dark matter distribution is indeed concentrated around this center of cluster of galaxies, but it is more extended like this. So this is an introduction of weak gravitational ranging. Okay, then I move on to the lens equation. So I think you have already learned lens equation as well. But I also try to explain this lens equation because, you know, learning same thing, you know, several times from different point of view may help your understanding of this subject. So I try to explain this lens equation. So lens equation is basically a master equation for gravitational lensing. We almost always start with this lens equation to analyze both strong and weak ranging effect. And this, maybe you have not learned general relativity, but that's not important. So what is important here is that we can derive, this lens equation is derived from this geodesic equation in general relativity that corresponds to a Newtonian equation on motion in Newtonian dynamics. So this is basically an equation of motion in general relativity. It looks like this, but I don't explain this equation, but this is the geodesic equation. And we can derive lens equation from this geodesic equation. And so this is the lens equation we derive from geodesic equation. And this is very simple equation. This beta equal theta minus alpha as a function of theta. And these vector are actually a two-dimensional vector on the sky. And this beta, in this figure, this is beta is here. And this is the position on the sky. That is a source position. like this. But due to the gravitational lens effect, light ray path is something like this. So we do not observe this object not at this position beta. So this is a source position. That means that this is the original position of this object, or we can also say that this is the position of this object that we would observe if there is no ranging effect. But due to the ranging effect, a light ray path is like this. So actually the position that we actually observe on the sky is this theta. So this theta is a image position. We call this an image position. That is a position that we actually observe on the sky. So this lens equation tells you that this source position and the image position are related by this equation. They are different by this angle alpha, which is a function of theta. And alpha. And the important thing is that this lens equation connect this deflection angle alpha with the underlying matter distribution. And in this case, the matter distribution of this ranging object, this. And so this is a slightly different view of this lens equation. As I said, this is a lens equation, and this explains the celestial sphere on the sky. So we are here, and our sky is like a sphere, as you know. So sphere is like sphere, but because we are interested in a small region on the sky, because this deflection angle is not like not very huge, much less than the, for example, degree scale. So actually, everything happens on a very small, tiny region on the sky. So if we focus on the small region on the sky, we can approximate this region by this Cartesian coordinate called theta 1 and theta 2. So we can assume that the sky is approximately flat. So we prepare this flat coordinate around the region we are interested in, and this is the two-dimensional flat sky, and so this is something what so this is just to repeat what I said. So this is the this beta denote the source position that we do not observe, but we would observe if there is no ranging effect, and this image position is the position that we actually observe. And they are connected by this angle alpha. And the important thing is that this deflection angle alpha is related to the underlying mass distribution. So it is actually written like this. This is the alpha is given by a convolution of kappa with some kernel. And this kappa is called a convergence, which describes the matter distribution. So definition of this convergence is like this. So this is the definition of convergence. This is a sigma divided by this sigma critical. And this sigma is this density profile of this lens rho integrated along the line of sight. So this is a projected two-dimensional surface mass density of this ranging object, normalized by some critical or fiducial surface mass density that only depends on the distance to the lens and source. So this is a dimensionless quantity, but essentially this describes the matter distribution in this ranging object. And by plugging in this kappa to this equation, you can calculate deflection angle for a given matter distribution of the ranging galaxy. So you can predict, so given some lens matter distribution, you can compute this deflection angle, and you can solve lens equation to study the ranging effect. So this is a very basic of the strong ranging or weak ranging. So this is just some quick summary of lens equation. So this describes a mapping between source position and image position. And the deflection angle is determined by the matter distribution of the lens, which is equivalent to this convergence kappa. Okay, so this was it was so far I discussed lens mapping for some specific position on the source plane, but now let's discuss lensing of an extended source. But this is very easy because given this lens equation, we can just consider this some small perturbation or the small deviation from the source position and image position like this. So for source position, I consider the small deviation from this central source position like delta beta. And we can say that this delta beta describes the shape of this source object. And I can also consider the corresponding small deviation from the center of the image like this, which I denote delta theta. And from this lens equation, I can easily derive this equation by Taylor expand this alpha deflection angle like this. So from this equation, I can derive the how the distant galaxy is distorted by lensing effect, which is given by this very simple equation like this. So this connects this relation between the shape of the source and the shape of the image. And these two are connected by this matrix A. And this matrix A is given by this equation. So important thing to note is that this A describes a mapping from image to source. So this is actually an inverse of the lensing effect. So in a sense, this is a kind of a de-lensing operation. So by applying this matrix A, we can convert the image shape to the source shape. And you can see that the inverse of this matrix A describes the standard lensing effect, how the source shape is deformed to the image shape by the lensing effect. So now let's see this matrix A in more detail. And this is not very obvious, but we can use this kind of relation. This derivative of this kernel is given by this Dirac delta function. And maybe this is difficult, but you can just plug in this equation to see that trace of this matrix A is given by this very simple form. And we find that we can find that this trace of A is written by this convergence that I explained, which is a dimensionless surface mass density. So in the end, we can derive this kind of equation. So this, again, this shows the mapping between the shape of the source and the shape of the image. And this matrix A is written by like this. So it is written by a convergence kappa and a shear that I newly defined in this slide, gamma 1 and gamma 2. So convergence is, like I said, this is projected surface mass density like this. And but this shear is also given by this convergence. This is a little bit complicated, but we can derive this gamma 1 and gamma 2 like this. And these are called shear. And if you look at this relation between delta beta and delta theta very carefully, then you can find the meaning of this convergence and shear, or how these convergence or shear change the shape of the distant galaxy. Because this kappa is described the uniform expansion because this kappa only have a value at this diagonal part of this matrix, and so you can find that by this, what kappa does to this the shape of the galaxy is that it uniformly expand or shrink the size of the galaxy. So this just changes the size of the galaxy. But because we don't know the intrinsic or original shape of galaxy, this effect is very difficult to measure. But this shear gamma, again, if you look at the original equation very carefully, you can find that this gamma 1 changes the shape of the galaxy like this. It size of the galaxy is shrunk along one direction, but it expands along another direction like this. And this gamma 2 is similar to gamma 1, but it is rotated by like 45 degrees like this. So both this gamma 1 and gamma 2 change the shape of the galaxy. It makes it add additional ellipticity to the galaxy. So this is what shear does on galaxy shape. And as I said, we can measure this shear by the statistical analysis of galaxy shape. So, so this is how to measure the shear. So I already explained this in a very naive sense, but this is a little bit more complicated explanation of how to measure the shear by using equation. So each galaxy have intrinsic shape like this, and we can approximately say that the observed shape of galaxy is given by the sum of the intrinsic shape, this one, and weak ranging shear like this. So observed shape is given by the sum of the intrinsic shape plus weak ranging shear. And we assume that the orientations of galaxies are random on average. Then this first part, intrinsic shape, approaches to 0 if we average over many galaxies. So if we add up this ellipticity for many galaxies and divided by the number of galaxies, then so this is the average of the intrinsic shape of galaxy. This approaches to 0. But and if we do this averaging for some part of the sky where we expect to share the same weak ranging signal or same value of gamma, then from this equation, this intrinsic shape part average out, and we can extract this tiny weak ranging shape. So again, this is same explanation. So what we do is measure each galaxy's shape in some sky region. So there are many galaxies, for example, in this region, indicated by this red circle. We measure the galaxy's shape in this region, and we take average of these galaxy shape. Then weak ranging signal shows up by averaging the shape of these galaxies. So this is a very basic of the weak ranging analysis. But the important thing is that this weak ranging shear signal is typically very small. So let's go back to this original equation. So this is the original shape of galaxy, and sum of given by the intrinsic galaxy shape and weak ranging shear. But typically, this intrinsic galaxy shape have a value of like a 0.3, ellipticity of about 0.3. But typically, weak ranging shear we are interested in is something like 0.03 or 0.003, depending on where you observe. But typically, we are interested in this kind of very tiny signal. So as you can see, this intrinsic galaxy shape is much bigger than the weak ranging signal, and that's why we cannot see this weak ranging signal but just by eye, and So in order to beat down this intrinsic galaxy shape, we have to average many galaxies shapes of many galaxies. So from this equation, I can estimate the signal to noise ratio. This is a signal to noise ratio, which is given by this. So this gamma is a signal, and the noise is given by this intrinsic galaxy shape. And by averaging n galaxies, we can reduce this error by a square root of n. But in order to have this signal to noise ratio to order unity, you can find, because of this large difference, you can find that we need a large number of galaxies, like a number of galaxies of like 1,000 or 10,000, in order to reduce this intrinsic galaxy shape and detect this weak ranging signal. Okay, so this is a quick summary of a convergence and shear. As I said, galaxy shapes are affected by weak ranging, and the convergence induces a uniform expansion of the shape of galaxies, but shear induces distortions. And this shear and convergence are connected with each other. So we can measure shear in observations by averaging many galaxies shape. So let's move on to how we extract the ranging signal from, for example, the cluster of galaxies. So to understand the, to get a qualitative understanding of ranging effect, this is a very simple or idealized simulation of ranging distortion. So what I did is just to place many galaxies on a grid and do a ranging simulation of ranging to see how the ranging changes the position and the shapes of these galaxies. So these are the simulated idealized galaxies. They are all have a spherical shape and are placed on this regular grid. And so this shows the image without any ranging effect. But once I place a very massive range potential at the center of this image, these galaxies behind this lens look like this. So as you can see, the position of these galaxies are changed following the lens equation that I mentioned. But you can also see that the shapes of these galaxies are also changed. And you can see this tangential, coherent tangential shape distortion around this lens center here. And you can see a very large distortion near the center of this object, but even for object apart from this lens center, you can still see some small distortion, distortion lens. So basically, this lensing induces this tangential distortion, or we often call tangential shear. So high density lens distort the shape of background galaxies along tangential direction. So we have a lens center here and draw a circle, and this distortion of galaxies are typically oriented along the tangential direction on this circle centered at the center of the lens. So this is again simulation, and in observation you can also see this tangential distortion feature in this arc. This is again these are strong ranging, but even apart from this strong ranging region, we have this coherent tangential distortion. So so this means that if we detect this kind of a tangential coherent tangential distortion, we can measure the lens mass distribution. So what we need to analyze, for example, cluster of galaxies is to measure the tangential shear signal around these clusters. So tangential shear signal is computed like this. So for a given reference point, and in our case, this should correspond to a center of cluster of galaxies. And we can define the tangential and cross shear for each galaxies by this equation. So again, this is a center of clusters. Sorry. Again, this is a cluster center of cluster of galaxies. And so this is some galaxies background of this quasar and located at some far from the center of this cluster. And for this galaxy, we can compute gamma 1 and gamma 2 from the definition of the shear. And for a given gamma 1 and gamma 2, we can compute tangential shear and cross shear for this galaxy following this equation. And this phi is just a polar angle of this galaxy in this coordinate gamma 1 and gamma 2. And this shows the meaning of this tangential and cross shear. So again, this I said this is the signal. We shouldn't observe this cross shear signal. So this must be consistent with 0. But if we get, for example, the measurement of this galaxy shape wrong, then this cross shear may be produced. So we often use this cross shear to check for any systematics in our analysis, measure this cross shear and find that this is consistent with 0, then okay, we can say that our measurement is probably okay. So we can use this cross shear for the checking of checking the validity of our analysis, and we use this tangential shear for measuring the mass distribution in cluster of galaxies, for example. And in order to, and what we do next is that we compare this observed tangential shear signal with expected signal, and to extract the information on the mass distribution of the lens. So from the theory, we can compute this tangential and cross shear like this. And tangential shear is actually given by convergence like this. So we can, for a given mass distribution, we can predict this tangential shear as a function of the theta. So this is a distance from cluster. So we can measure this tangential shear as a function of distance from the cluster center like this. And on the other hand, we have observed tangential shear from the data. And by comparing this observed shear and computed shear, we can say that this assumed kappa is correct or not. And what we actually do is that we assume some parameterized form of this convergence kappa and try to fit observed theta to extract parameter on this convergence kappa. So I will show some specific example in the next slides, but this is what we do in our analysis. but so this is a little bit advanced, but the share important thing is that the share is non-local. That means that so this is what share at this position theta, but this share signal depends on the all the matter distribution within this radius theta. So by measuring the tangential share around here, we are not just probing the matter distribution around here, but we are probing all the matter distribution inside this circle. So this is a quick summary of the tangential share. So gravitational ranging induces coherent tangential distortions around the length, and tangential share at some radius depend on the integrated mass within that radius. So from which we can extract the information on the mass of the ranging object. So, and this cross 45-degree rotated share should vanish. So we can check the systematic errors from the analysis of this cross share. Okay, now I will explain how we measure the tangential share signal for cluster of galaxies. Maybe you know what is cluster of galaxies, but so this is a very quick explanation of cluster of galaxies. So we are interested in cluster of galaxies because cluster of galaxies is a very massive concentration of dark matter. So so this is indeed a very dark matter dominated system. So this is a very useful site for studying dark matter. But so this is from numerical simulation of dark matter. But in observation, we can detect this cluster of galaxies. For example, concentration of red galaxies. So this is a real image of cluster of galaxies. And as you can see, there are many galaxies with very similar color. And so we can find cluster of galaxies on the sky from, for example, the concentration of these galaxies with very similar color. So as I said, cluster is a dark matter dominated system. And so that means that we expect a very significant gravitational ranging signal. So this cluster of galaxies is a very ideal site for studying dark matter using both strong and weak ranging. But in this lecture, I'll focus on the cluster weak ranging and show a specific example on how we analyze tangential share and extract information on the mass of the cluster of galaxies. So as I said, in order to do the weak ranging analysis, we have to measure the shape of each galaxy's shape. And this is a very technical and advanced topic, so I do not explain this in this lecture. But I just say that this is not a very easy task because this is the intrinsic galaxy shape, and this shape is affected by many observational effects like atmospheric smearing and also the pixelization and also the noise. So in the end, what we observe is something like this. So this is a shape, this is the image of each galaxy that we use for weak ranging analysis. And this is very faint and, still okay, but it's, as I said, we really want to measure very accurately measure the shape of these galaxies. So this is very challenging task. But the nice thing is that we can simulate all these steps. So for example, we can do some sort of a simulation to generate these fake or mock galaxy images and analyze by our method to see we can to make it more accurate. But anyway, so this is an advanced topic, and I do not explain in detail. So suppose we successfully measure the shapes of each galaxies, shape of each galaxy. What we do next is to measure the tangential shear. So tangential shear signal is measured like this. So as I said, reference point is always a center of cluster of galaxies. So we take center of galaxies as a reference point and prepare some annulus with some radius theta. So for some theta, we prepare some this kind of annulus with some finite radius. And we take all the galaxies within this annulus. And the definition that I just mentioned. So for each galaxies, I can compute the tangential shear. And what I do is to take the average of the tangential shear of each galaxy like this. And in weak ranging analysis, we usually introduce this weight because some galaxies are brighter and we can measure the shapes better. And some galaxies are very faint and it's very difficult to measure their shapes. So we are giving more weights on the galaxies that are brighter and we can measure their shapes better. But anyway, so we can just take an average of this each galaxy tangential shear for each galaxy with some weight to get the average tangential shear for this annulus. And we can also estimate the error on this average tangential shear by this equation like this. Then we repeat this analysis for different radius and different annulus. So I will show some example from this cluster, and this is a cluster that was observed by our group and published in this paper in 2012. And this cluster was observed with Subaru Supreme Cam. And Subaru telescope is a Japanese telescope located in Hawaii, and this is a very ideal telescope for weak ranging analysis. But anyway, so I'll show example from this Subaru Supreme Cam image. So this is a real image of Subaru Supreme Cam. So this is a center of cluster. And maybe it's very difficult, but you can see some extended large arc like this. So this cluster shows some strong ranging feature like this. But the Subaru can cover a very wide field of view. So it can observe cluster out to a very outskirt of this cluster. So this is the image of the cluster, and these circle indicate all the galaxies that I used for the weak ranging analysis of this cluster. So as you can see, we can derive this tangential, which is this, and with this error bar. So as I said, this is tangential shear, red one is tangential shear, and you can see that this tangential shear is non-zero for all the so that means that this tangential shear signal is significantly detected, and this tangential shear signal is detected all the way to the more than 10 arc minutes from the cluster center. And this blue cross shows the cross shear And as I said, we don't expect this cross shear to be detected. So we use this cross shear for checking any systematic effect in, for example, in measuring the galaxy shapes. And in this analysis, you can see that this tangential shear is consistent with 0 for almost all the beams. That means that indeed this cross shear is consistent with 0 as expected. So we are so this is kind of a sanity check, but we are doing the right analysis. We can say that we are doing the right analysis from this cross shear. So as I said, in order to extract the information on the cluster, like cluster mass or the density profile, we have to compare this observed tangential shear profile with a model. And in this lecture, I explained two models. One is this SIS, and the other is this NFW model. So one is a singular isomorph sphere model that is still very commonly used in our community. So this has a very simple density profile. So this is a three-dimensional density profile written like this. So this is a density as a function of the distance from the lens center in 3D. And this profile has a power law shape, and this density is proportional to the R to the minus 2. And as I said, this convergence used for lensing is a projected density profile along the diagonal side. So I have to project this three-dimensional density profile along one direction to get this convergence profile. And the convergence profile is written like this. It is proportional to the distance inverse of the distance from the cluster center. And this is because this is R2 minus 2, and by integrating this to some direction, I get some additional power, and this R2 minus 2 become to R2 minus 1. So this is a consequence of projecting this 3D profile along diagonal side. But anyway, so I have this convergence profile. And actually, we can also see that this tangential shear profile is very similar, written like this. So in this SIS case, convergence and shear profiles are very similar like this. And this prefactor is correspond to the Einstein radius and is given by this like this. This sigma is a velocity dispersion, and d denote distance to the between lens and source and observer to source. But anyway, important thing is that SIS profile have this kind of a density convergence and shear profile. So this is a result comparing the observed tangential shear profile with the model fitting with SIS. As I said, this SIS profile have a power shape. So we have a freedom to change its normalization. And this is a result of fitting. And by fitting to this observed profile, I can, for example, constrain the velocity dispersion of this cluster, which is like 1,200 kilometers per second. And so this is indeed very large and correspond to the cluster mass of more than 10 to 15 solar mass. So from this weak ranging analysis, we can infer the mass of the cluster. So another approach is to use this Navarro-Frank-White NFW profile of this doubled power law shape. At the inner region, these have the this density profile proportional to the R2 minus 1, and in the outer region, this density profile proportional to R2 minus 3. So this is quite complicated, but actually there is an analytic expression of tangential shear profile is available. So we can use this analytic expression for the analysis. So this is similar to the SIS fitting result, but here I just use this NFW profile. And you can see that we can again fit this observed tangential shear profile pretty well. And from this fitting, we can again infer the cluster mass, and we can find that is about 10 to 15 solar mass, and find that this cluster is very massive. So this is the summary of the example of analysis. Tangential shear profile can be measured for each massive cluster by measuring the tangential shear for each annulus. And by fitting observed profile with a model, we can extract information on dark matter distribution, such as total mass. So finally, I will quickly go through this weak-ranging mass map stuff. Because this is a little bit advanced topic, but still very interesting. So I just try to outline the science we can do with this weak-ranging mass map. So as I said, this tangential shear profile analysis have to assume the center of each lens for fitting, but actually we can do this mass reconstruction without assuming any a priori, for example, position of cluster from weak-ranging data. This has been shown by Nick Kaiser and this Gordon Squires. And so again, this is complicated, but this is what I said. So this shows the relation between convergence and shear. This shear gamma 1 and gamma 2 is written by this convergence, convolution of convergence with some kernel. And so this indicates that we can invert this relation to obtain this relation. So this is a relation between, inverted relation between shear and convergence. Convergence is given by this. This is a complex representation of this shear, and a convolution of this shear with some kernel, we can get this convergence. So this shows some example of this mass mapping. So again, this is the same cluster that I used for the tangential shear analysis. And again, this is all the galaxies I use for weak-ranging analysis. And for each grid on the sky, I can average shapes of each galaxies to measure the shear on this grid. And to repeat this, I can create a map of this shear on the sky like this. And by using the equation that I mentioned, I can convert this shear map to the convergence map. So this is the reconstructed convergence map. So this shows the contour of this convergence, and this region is a high convergence region. And so you can see this strong ranging feature, but from this weak ranging mass map analysis, we can confirm that this region is indeed a very high dark matter density region. So we are using this kind of technique to current ongoing survey data. This hyper-Shublingham survey is a survey conducted by a telescope, conducted using the Subaru telescope. PI is Satoshi Miyazaki at NOJ. And so we are using a new wide field camera mounted on the Subaru, and we are observing the sky over 1,000 square degree of the sky to 26 magnitude depth. And so this survey is really ideal survey for weak ranging analysis. So we are using this survey data to draw a very wide field mass map. So this shows just one example. again, by averaging the shape of galaxies on the sky, we can reconstruct the shear map like this. And by using the equation that I mentioned, we can invert this shear map to the convergence map like this. So this is the convergence map, or as I said, convergence is a projected surface mass density. So this is just a projected dark matter distribution on the sky. And by doing this, by extending this kind of analysis, we can also reconstruct the three-dimensional mass reconstruction. Because we observe many galaxies, some galaxies are located nearby and some galaxies are located far distant. So we can do, we can reconstruct mass map for using galaxies at different distance from Earth. And by doing some manipulation, we can reconstruct the 3D mass distribution. So this is the 3D mass map we reconstructed from HSC data. And this is actually the largest 3D dark matter mass map ever created. So we can do this kind of analysis and study the dark matter distribution. And we also studied how the dark matter distribution evolve with time. So this is the summary of this lecture. So as I said, weak gravitational ranging provide a very powerful means of studying dark matter distribution. And a key quantity for this weak ranging analysis is convergence and shear. Convergence corresponds to the projected surface mass density, and but we cannot directly measure this convergence. What we measure is shear, which corresponds to the distortion of vacuum galaxies. We can measure this shear by averaging shapes of many galaxies. And as I said, we have to use many galaxies in order to get accurate weak ranging measurement. So, so in this sense, weak ranging analysis is very expensive. We need a very wide field image and with sufficient depth to observe many galaxies and to resolve shapes of many galaxies. But because of the advance of the astronomical observations, for example, the Hubble telescope is rarely ideal telescope for this weak ranging analysis. We can observe many galaxies for a very wide field of view. So weak ranging is rarely weak ranging is now is advancing very rapidly, and we can use this weak ranging technique to really precisely measure the dark matter distribution as a function of cosmic time. And we are using this weak ranging to try to understand the nature of dark matter and dark energy. So I think this is the end of the lecture. So thank you very much.
Okay, thanks Oguri-san for your great lecture and your clear explanation. So now I would like to invite the participants to ask Oguri-san directly. So I will invite Suzu from China. Are you there? Suzu? Hello?
Yes, I'm here.
Okay, yeah, you can ask him directly, please.
Okay. Okay. It is used to measure the matter distribution in the reverse, or and to do something like to study the large scale structure or something else. I don't know. Maybe it's Maybe it should be like this. Is it used to map the matter distribution, mass distribution in the universe? And what can we learn from that?
Yeah, right. So as you know, the dark matter distribution, we cannot directly observe the dark matter distribution by pointing the telescope, but by using this weak ranging, we can, for example, measure the amount of dark matter and also the distribution of dark matter. I mean, how clumpy they are distributing. So as you know, the universe has large scale structure and they are inhomogeneous, right? So they have there is an over this region and under this region on the sky. And we can already see this kind of inhomogeneity by observing galaxies. But it's very hard to observe this density inhomogeneity of galaxies. No, density homogeneity of dark matter. And this weak ranging can allow us to directly measure this density inhomogeneity as well by analyzing this very wide field, this kind of very and from this we can measure the density fluctuation of dark matter as a function of time. And for one interesting application is that we can check if this dark matter density fluctuation is consistent with, for example, the fluctuation we can observe from the cosmic microwave background. So I'm not sure if you have learned this cosmic microwave background or not, but we can also measure this density fluctuation at a very early universe with this cosmic microwave background. So in a sense, we know the initial condition of the universe. And from this very early time, this density fluctuation grows with time because gravity is an attractive force. So if there is a small inhomogeneity over this region, have a stronger gravitational force, so that they try to gather with each other. So this density contrast increase with time. So this density fluctuation evolve with time. So actually this is seen in this picture. This is a lower redshift. That means more time close to Earth. And this is correspond to more distant universe. And the density fluctuation is more prominent in the later universe because of the growth of the structure, And we can also study this growth of structure from galaxy distribution, but this is indirect because we have to assume the relation between galaxy and dark matter. But by using this weak range, we can directly measure how this density inhomogeneity grow with time. So this is one important application. And by studying this growth of the density fluctuation, we can infer for example, the property of dark energy. If dark energy is consistent with a cosmological constant, or other models is correct, or
yeah. So you just mentioned that there are some shears can be classified by tangential shear, and which is by lensing, and another is cross shear.
yes.
But you didn't provide anything that should blame for this cross shear. So what is it? which things that cause the cross shear. I may want to know about that. Thank you.
Yeah, cross shear is not. So cross shear is usually not generated by lensing. So how to say? So this is used to make sure that you are doing right analysis. You know, so this must be zero. So if we, for example, sorry. So this must be zero, and in this case, this is indeed zero, right? So, okay, then I can say that, okay, I'm doing a right analysis. But if this is significantly non-zero, then this is something you shouldn't observe. So you are doing something wrong. So, so what I'm trying to say is that we can, so this is not generated by lensing, and there is no other, you know, physical kinds this cross shear. So that means we shouldn't observe this signal. So this cross shear signal is used to make sure that you are doing the right analysis. So this is what I meant. So am I answering your question?
Yeah, I think so. I see.
Okay. Okay.
And thank you. You have a nice background.
Okay. Thank you.
So beautiful.
Okay, thanks, Zuzu. And then there is Sulis, but she don't have any microphone with her now, so maybe I can read it for you. How do we differentiate if the distortion is due to weak lensing or due to the shape evolution or intrinsic shape of the galaxies themselves?
How to distinguish?
Yeah, how to differentiate?
Right. So that important.
Yeah, it's technical. Easy.
So basically, what we observe is a galaxy shape that is both affected by intrinsic shape and weak lensing. So, so this just says that we observe the sum of the intrinsic galaxy shape and also the weak lensing shear, and we try to separate this intrinsic shape and weak lensing shape by average many galaxies shape, like this, assuming that assuming that the orientation galaxies are random on average, like this. So if this assumption is completely correct, then we can average many galaxies shape to really separate this intrinsic shape and weak lensing shape. But in fact, this assumption is not really correct. and orientation of each galaxies are correlated. So intrinsically, orientations of each galaxies are correlated, and in more advanced analysis, we have to take account of that effect actually. So this is a very advanced topic, and I do not go into detail, but this is very important. But one important thing to say is that in the case of a cluster weak lensing, so I analyze this cluster weak lensing. This shear signal is actually quite strong, even though this is a weak lensing. So in this case, this intrinsic correlation of the galaxy shape can be safely neglected. But in the case of a more, weaker lensing analysis like a cosmic shear. For example, we can study the large-scale structure using the two-point correlation function of galaxy shape, which is called a cosmic shear. And in that case, this intrinsic correlation of galaxy shape actually cannot be ignored. So we have to take account of that effect and try to separate them with weak ranging signal. But this is a very, technical and advanced topic. So I do not go into detail.
Okay. Yeah, thanks for your answer. And then I will invite Fernanda Putra Pratama. Are you there, Fernanda?
Yes, I'm here.
Fernanda, sorry. Okay, please.
Okay. Thank you for the opportunity and for the interesting lecture. Okay. So I have two questions that I think may be related, and I'm sorry if you have explained this before, but I'm still wondering, is it possible to get cross shear image because the object that we observe has more than one lens. Yeah, is it possible somehow, or
Yes.
we shouldn't get any?
Yeah, that's a very good point. And so this is again, this is also advanced topic, but a very important point. And so this shows the configuration of gravitational lensing, and lens is here. And so in the case that there are two lenses, if these lenses are located at the same redshift or the same distance from observer, like here and here, then even in this case, cross shear is not generated. But if this lens is located at a different position along the line of sight, for example, if there are two lenses here and here, then actually this cross shear, small, it is not very large, but a small cross shear can be generated. So actually, yeah, physically there is a way to produce this cross shear. But even in that case, this cross shear is very small compared with the tangential shear. So that you can still use the cross shear to check this analysis. Okay, like this.
Okay, more question from Fernanda?
No, I think that answered my question. Thank you so much.
Okay, yeah, thanks. And then I will invite Naman Bajai from India.
Thank you, Professor, for the wonderful lecture. I wanted to know if we can differentiate between gravitational lensing by a black hole and that by a clump of dark matter, because both are invisible to the telescopes and they both have gravitational effects on the surrounding, and only gravitational effects on the surrounding.
Right. So basically, if we measure the profile in principle, if we measure the profile very precisely, then we may be able to distinguish them because, so this is a tangential shear profile, right? And this depends on the matter distribution, like I said. So by fitting this, we can constrain the density profile. For example, this is a case. This is, for example, this singular isothermal sphere case. This tangential shear profile is proportional to the distance inverse of the distance. But I mean theta to -1. But in the case of a black hole-like object, I think this tangential shear profile should be more steep, like theta to -2 or so. So if so this is in principle, and it's so in principle. So, but in theory, if we measure the tangential shear profile very precisely close to the black hole, and check the slope of this tangential shear profile, we can say if this is more like a black hole or a galaxy like. Yeah. So this is the answer.
Thank you. Thank you.
Okay, we have at least 2 questions left. The first one from Muhammad Rafif Rabbani, please.
Yeah, okay. First, I would like to thank you, Doctor, for the very amazing lecture. I have 2 questions. The first one is, you mentioned that the cross share is used to check whether there is any systematics in the analysis. So I'm just curious, what would be the cause for those systematics?
Okay, so yeah, like this. So one important systematics is that so this is a complicated technical thing. Is that when we observe galaxies by using some telescope, this shape of the galaxy is smeared by the so-called PSF, point spread function. So because of the finite angular resolution of the telescope and atmospheric turbulence, this galaxy images are smeared by like this. So we have to correct for these effects by measure the original shape of galaxy like this. So this is observed galaxy, and we correct this point spread function effect to get this, to infer this. And we do this by measuring the shape of the stars, because stars are very compact. It should be like a data function on the sky, but because of the limited resolution of the telescope, it also looks extended like this. So this gives you the shape of the PSF, point spread function, and we use this information to correct this effect to infer this shape of galaxy. But if we get this procedure wrong, I mean, this estimate of the point spread function is very inaccurate, then it can produce a significant, cross share, because this PSF point spread pattern of this point spread function on the sky can have this kind of a cross share like pattern. So that sometimes we observe this large cross share because of the imperfect correction of this point spread function effect. So this is the answer.
Okay, thank you. My second question is, in this lecture, you mentioned mainly about weak lensing analysis for galaxies, but I read that people had done weak lensing analysis for the CMB. And could you please explain to me how it is done? And does this mean that we can map the entire mass distribution up to the last scattering surface?
Right. Yeah. So this weak lensing is also this weak lensing technique is also used for the cosmic microwave background to measure the weak lensing signal out to the last scattering surface. And in the case of a CMB, they don't have this kind of shape. So we use this original lens mapping, change of the position between this theta and beta and theta. So this lens equation is also true for the case of the CMB lensing. And as you know, the CMB pattern is very, very well known. It is a Gaussian like distribution. It follows very well follows the Gaussian statistics. But if this ranging effect applies, then this CMB map is distorted following this Lenz equation. And as a result, this ranging map becomes non-Gaussian, and it deviates from the expected Gaussian distribution. And we can use this kind of feature to extract the ranging effect from the CMB map. So this is quite different from the weak ranging analysis that I mentioned in this lecture. But this range equation is of course same. So we can extract information on the deflection angle. And so that means that we can extract information all the way to the last scattering surface. But as I said, this deflection angle depends on the convergence. And the convergence is a projected mass distribution, right? So what we can get from CMB is all the projected mass distribution from Earth to CMB. So of course, this weak ranging of galaxies and CMB are very complementary. By using both CMB and weak ranging, we can get this convergence as a function of redshift at very different redshifts, so that we can reconstruct the 3D, in principle, reconstruct the 3D matter distribution and study the evolution of the density fluctuation. So in this sense, CMB ranging is also very important. But of course, I didn't have time to explain that in this lecture. But yeah, it's very important topic.
Okay, maybe there is the last question from Mrunalini CP from India.
Yeah, thank you. I got my answer from the last question. I don't have this question. I just want to ask how far we can observe the weak gravitational lensing, and you have answered the last answer. Thank you.
Okay. 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 Maybe this session I need to stop until here. Thank you very much for Oguri-san, Dr. Masamune Oguri. Thanks for your great lecture, and then thanks also for the participants who are joining us in this lecture. Before we stop this Zoom meeting, maybe we need to take our picture together. Okay.
Oh, okay. Group photo.
Yeah, group photo. Okay, I will invite you all to open your video. As usual, we will take a group photo together. Okay, let me check for the, oh, there is someone in the car. Okay. Okay, I will take for the first slide. Okay, 1, 2, 3. Okay, second slide. Wait a minute. Second slide. Wait. Second slide. Okay, thanks everyone. And now I wanna invite you to open your microphone and say thanks. Big applause for Oguri-san.
Thank you so much, Prof. Oguri. Thank you very much, Professor Masamune Oguri.
Thank you,
Hi,
Professor.
Oguri-san. How are you? Permada here.
Hi.
Good to see you again. Thank you very much.
See you. Yeah.
Been very many years.
Okay, thanks everyone.
Yeah, thank you everyone.